All right, morning. I'm your Huan Yang from here and IQC. So today I'll tell you about a revolution in astronomy that's happening right now. As many of us have heard, on February the 11th, LIGO Scientific Corporation has announced the first direct detection of gravitational wave in human history coming from a binary black hole system. So this marks the beginning of gravitational wave astronomy. And from now on, we shall be able to probe our universe using both long-range forces in nature. So I'm sure a lot more discoveries are waiting for us in the near future. So what are gravitational waves? Just like electromagnetic wave is a prediction of Maxwell's theory, gravitational wave is a key prediction of Einstein's general theory of relativity. It was discovered by Einstein about 100 years ago. So according to general relativity, a massive object would distort the space-time nearby. So if masses are moving and accelerating, these space-time distortions would propagate out as waves, and these waves are gravitational waves. Mathematically, the strain of gravitational wave, which measures the fractional change of length, is proportional to the second-time derivative of the quadrupole moment of the source, and inverse proportional to the distance between source and observer. And this numerator here is also roughly proportional to the mass and velocity square of the source. And that's why gravitational waves are maximized from those fast-moving, massive objects in binaries, such as binary black holes or neutron stars. So gravitational waves propagate at the speed of light with two polarizations. So if a wave is propagating towards me, it will squeeze an object in one transverse direction and stretch it in the other transverse direction. And we can rotate the whole pattern by 45 degrees to obtain the other polarization. Gravitational waves also exist in a broad frequency band in our universe. It could come from quantum fluctuations in early universe, or mergers of massive black holes or stars, or so on. So in particular, the ground-based detector, which just made its detection last year, mainly targets the merger of stellar mass black holes and neutron stars. And people have also built or proposed other detectors to detect waves at other frequencies. Right now, it's like the time when Galileo first used optical telescope to study astronomy. And these detectors are like the gamma ray, X-ray telescope that were invented later on. So based on the past success of astronomy and how all those great discoveries were found with all the electromagnetic telescopes, I think it's safe to say that this gravitational wave astronomy has just shown us a tip of an iceberg. So with gravitational wave observations, we will be able to tackle many problems related to the physics of compact objects, such as black holes and neutron stars. We will also have better understandings for some of the fundamental physics problems, such as whether primordial gravitational perturbations are quantum, and whether general relativity still works in the strong gravity regime. Also, with new observations, we are likely to be able to raise new questions, and we may also have unexpected discoveries, just like what we had with all the famous telescopes in the past. Okay, so with this rapid expansion of gravitational wave astronomy, also provides provides us great opportunities, but also impose great challenges. So in the near future, we will have more and more frequent gravitational wave detections, but then we have to work on detectors to try to improve their sensitivities to fulfill the growing needs. And we will likely have much better understandings about the physics of black holes and neutron stars in the near future, but then we're likely to face many puzzles and challenges from the incoming data. So in this talk, I will discuss both how to detect gravitational waves and the physics of their sources based on my own research. So I will be mainly focusing on waves at frequency 1 Hertz or higher, and the corresponding ground-based detectors, such as LIGO. OK, let me start with detector physics. So as we can see from this map, there are already a few detectors. Sorry for the colors here. There are already a few detectors being built, labeled by these yellow stars. The ones under construction or proposed for future are labeled by these red stars. So with a global network of these detectors, we will have a better sensitivity on a given gravitational wave event. And we will also have the ability to localize the source in the sky. So all those detectors have very similar designs. So let me just pick the current most sensitive one, the LIGO detector, as an example. So LIGO is basically a Michelson interferometer. Okay, so more than 100 years ago, a Michelson interferometer was used to disprove the existence of ether, and that led to the discoveries of special relativity. And last year, another Michelson interferometer just made us the first detection of gravitational waves. So this one has 2 arms, and the arm cavity length is about 4 kilometers. And each arm cavity has 2 mirrors, 40 kilograms each. So when the gravitational wave comes in, it will stretch one arm and squeeze the other arm. And this interferometer basically measures the differential arm lengths to infer the strength of the gravitational wave signal. So in the LIGO detection band, the typical magnitude of a gravitational wave is about 10 to the minus 22, which means that it changed the arm length to about 10 to the minus 19 meters. We notice this is an extremely small number because it's even 10,000 times smaller than the size of a nucleus. OK, so as we mentioned earlier, the strength of a gravitational wave event is inverse proportion to the distance between the source and observer. So if we can improve the sensitivity of the detector by 10 times, we can actually probe the source 10 times further away. Because the merger rate of these compact binaries is roughly constant in a fixed volume in our universe, that means the event rate will be boosted by 1,000 times. Also, with better sensitivity, we can measure the probability of a given source with better accuracies. So there is a strong motivation to improve the sensitivity of detectors. There is also a concrete plan to upgrade LIGO. Right now, the advanced LIGO is still taking data. Probably it will last for several years until 2018. So around the same time, the experimental research for different parts of advanced LIGO 1.2 or advanced LIGO Plus is still ongoing. And the theoretical study for the next generation LIGO, the so-called LIGO Voyager, has already started. So we have about like 4 or 5 years until these experimentalists start to test out the theoretical proposals.
Could you go back one slide?
Sure.
Talk about those event rates a little bit. What are the big uncertainties now in the event rates?
Yeah. So
is that what you mean by that?
Yeah. So yeah.
And how quickly are they going to converge?
So based on these, how fast we detect those events last year,
yeah.
I would imagine we will push the event rate to the high end. Yeah. So in the past, we are quite uncertain how likely it is.
Black holes.
Yeah. Yeah.
But so can you say a bit more quantitatively? Is that lower limit going to go from 10 to the minus 4 to 10 to the minus 1 in the next year?
Yeah, for binary black holes, it's never definitely going to be like this order. It's not going to be this order for sure.
Yeah.
Yeah.
Okay.
Yeah. The uncertainty basically, people have models of this how you make these binaries in the globular cluster. It's because especially for this black hole system, you cannot observe it in the past, so there's big uncertainty. Okay, so part of the current developments focus on reducing different noise sources in LIGO. As we can see from this plot, so in the detection band, the dominant noise source is mainly the optical quantum noise labeled by this red curve, and the coating thermal noise labeled by this purple line. So I shall briefly discuss these two noise components. Okay, so first, as a theorist, in an ideal world for me, this mirror surface would be completely flat, and this wavefront of laser is Gaussian. Okay, but later on, I was reminded by my experimentalist friend that in reality, the lossy coating materials would generate random thermal fluctuations of the mirror surface, and this distorts the laser wavefront and introduces additional position noise. And this is the origin of actually the coating thermal noise. So if we want to reduce this noise, of course, one way is just try to find better coating materials with better quality factors. But it's difficult. The other way is try to come up with better coating designs such that we minimize the combined noise from different layers while keeping the total reflectivity to be the same. So we did optimization before, and it could give about 7% of reduction in noise, and which is about 20% boost in event rate. So this is a small number. We were actually quite surprised because we showed the previous calculation in thermal noise actually have a much bigger uncertainty. I think the reason is mainly because only there is one type of material, tantalum, which gives most of the noise. So it turns out that it doesn't matter what your design is for the current material. But in the future, when we have better materials, I think this coating optimization method will give better reduction in noise.
Why does increasing the quality factor? What do you mean by quality factor? Is it the with oscillations?
Yeah. So there is a thing called fluctuation dissipation theorem.
Sure.
So if a material is more lossy, so it is more dissipative, then the noise is higher. Yeah. So we want material with higher quality factor. Okay, so on the other hand, we can with stronger laser power, and more massive mirrors and better optical designs, we can actually achieve a factor of 3 reduction for this optical quantum noise. This is quite important because this means that for the kind of binary black hole sources we detected last year, we will be able to see more cycles here. And also in this high frequency band, we will definitely be able to see more neutron star binaries.
So sorry, you're saying this increase in sensitivity is just due to the coating, improving the coating?
So you have to combine them all.
Okay.
Yeah.
What are the factors which cause that increase in sensitivity?
Are you talking about here or the previous one?
This one.
Oh, this is with stronger laser power. Laser power and more massive mirror, and most importantly, you have better optical. You add in a filter cavity here. It's a much better optical design. You have squeeze light injection as well. So yeah. So this is about the optical quantum noise part. It's not.
But that's also your work.
Yeah. Okay. So I've discussed the experimental front of the detectors, and it turns out that these detectors can also do other kind of cool physics. So this is related to the fact that LIGO is actually a quantum measurement device. So what do I mean here? So as I mentioned earlier, the displacement sensitivity of LIGO is about 10 to the minus 19 meters. If we compute the de Broglie wavelengths of the test mass in LIGO, we actually arrive at similar numbers. So this is interesting because this means that LIGO is so sensitive that it's able to measure the quantum mechanical position uncertainty of the mirror, of its mirrors. This is also very non-trivial because such mirrors contain more than 10 to the 27 atoms. And usually we're more familiar with quantum tests for one or few particles. And when it comes to such a human scale object, a lot more questions may arise. For example, is quantum mechanics still valid in such a large scale? And how do we understand this classical to quantum transition? And how do we prepare the quantum state for such macroscopic object? So in order to answer these questions, the development of LIGO has spun off a series of experiments targeting the quantum mechanics of these macroscopic objects. So these experiments basically use similar languages and techniques compared to these quantum optics experiment, but the test mass in these experiments have ranges from nanograms to kilograms, and also they all contain enough number of particles to be viewed as macroscopic object. So let me discuss one application of these experiments is related to the question that whether gravity is intrinsically quantum or classical. So this is a long-standing problem, and there is tremendous effort on this, and we had a lot of progress. A lot of that happened here, but unfortunately, we don't yet have a conclusive answer. So if we look back into the dark ages of quantum mechanics, like before quantum mechanics was discovered, there were actually the experiments, like the measurement of black body radiations or the discoveries of photoelectric effect, which led to the correct theory, the correct quantum theory. So if we borrow that experience, we might argue that any possible indication from experiment here might also be helpful. So let us imagine a Gedanken experiment, and let's say we have a scale, an even scale, and we put it in a uniform gravitational field. Then we prepare a test particle in a Schrodinger cat state, and we put it on the scale. So let's suppose gravity is quantum. So in this case, the gravitational field will co-evolve with the quantum state of the particle, and they together form a Schrodinger cat state. So after some time, the scale will become uneven. Okay. So on the other hand, if gravity is classical, so let me assume it satisfies the so-called semi-classical gravity model, such that the Einstein tensor equals to the expectation value of the quantum stretch energy tensor of matter. So in this model, the gravitational field is classical. It will be the same as if we have half mass particles on each side of the scale, and the scale will remain even at all times. So apparently, the experimental signatures are different in these two proposals.
So,
yeah.
I mean, are these two really different per se? I mean, you could have a theory of quantum gravity that has a semi-classical limit, and what parameter is telling me in which case? I mean, these could both be in a theory of quantum gravity.
Yeah, so it turns out, so Hu and his student actually wrote a paper about this model last year. So what they claim is this model is not, I mean, it's not a quantum gravity taking the classical limit. It's not, yeah. It's very different.
Is that the old objection from somewhere at 1980 that equation is actually unstable?
So there are many debates about this kind of model. For example, if we look at this equation and if we assume the wave function Cobb's description is true for quantum measurement, then we will see that once we have performed measurement, the right-hand side will no longer satisfy the usual equation motion for matter, and the left-hand side will no longer satisfy the Bianchi identity. So there is tension, and also Don Page argued that, and he actually did the experiment. He argued that if we say the manual explanation is true, then this is also in tension with that. And I think Diossi and others try to use this model to explain the wave function Cobb's. But here, I think, I mean, this problem is like a mixture between this modification to quantum mechanics. Also includes this interpretation of quantum measurement. It's unclear to me that what will be the ultimate true interpretation for quantum measurement, and I think it might be a good idea to just try to keep an open mind to other possibilities and try to push it a little bit further, like in addition to those arguments. Okay. All right. So in order to maximize that semi-classical gravity effect, it turns out that it's better to use those macroscopic, massive oscillators, not those small particles, because the gravity effect will be stronger for this object. But it's not easy to prepare such object in a Schrodinger cat state. Luckily, it turns out that this semi-classical gravity effect already exists for a simple harmonic oscillator, such as LIGO mirror. Okay, so if we prepare such object in a so-called displaced squeeze state in the phase space, so this is a quantum state. This is a position uncertainty. is the momentum uncertainty. One can show that without this gravity, semi-classical gravity effect, this quantum state will rotate in the phase space under the influence of this harmonic potential. And this orbital frequency and spin frequency will be the same. They're both equal to the harmonic frequency of the oscillator. Now, if we, with the presence of this semi-classical gravity effect, then we can show that this orbital frequency will remain the same, but the spin frequency will somehow be faster, will become faster. So if we can do a state tomography here, then in principle, we can measure the difference. On the other hand, if we shine laser on the task mass, we can also so we without this this semi-classical gravity effect, we will see the noise peaks due to thermal noise and quantum radiation pressure noise. They should be all resonant at this harmonic frequency. But with the presence of this semi-classical gravity effect, one can show that the noise, thermal noise will be resonant at this orbital frequency, but the quantum noise will be resonant at the spin frequency. So we can observe a split of these noise peaks. So this will also be a smoking gun of this model.
Is this shift in the spin frequency occurring because of the interaction of the two mirrors, gravitational interaction?
It's the self-gravitational effect. It's basically
Self-gravitation.
Yeah. So the motion change under its own gravitational field. So it turns out that the self-gravitational effect is stronger than the mutual gravitational effect.
Since your detector is a massive option, how do you screen out decoherence?
Yeah, so this model doesn't really assume gravity decoherence. But if we want to test gravity decoherence, this kind of object is actually better than those microscopic particles, because these detectors have low frequencies, it's more massive. It can actually provide better tests for gravity decoherence or other quantum gravity models. So if you have if you have any idea or like what model you want to test, just come to me. My office is in 464. Okay. All right. So yeah.
Question. So what is the conclusion? So did you test the semi-classical gravity or not?
So yeah. So conclusion is it turns out that it's much easier to use this device to test out these semi-classical gravity model. And it seems to be within the reach of current experimental technology.
But it's going to happen in the future. It hasn't been done.
It will happen in the near future. I hope.
At LIGO. Will it be at LIGO?
LIGO will be a better choice, but I'm not sure if I can convince them to do this instead of detecting gravitational waves. But there are other tabletop experiments. Yeah. Okay, so I've talked about the detector physics and their applications in study more fundamental physics. So now I will switch gear and I'll talk about the astrophysics of compact objects, which also generate gravitational waves. So this is a very broad subject. It has many different kind of systems and very rich phenomena. So I'll only pick black hole systems as example to illustrate the space-time dynamics and the gravitational wave emission and the EM electromagnetic signatures in the strong gravity regime. So let me start with the binary black hole system. Okay, so this is a real data from the event last year, the GW 150914. So let's try to understand this waveform. it turns out that this waveform can be divided into 3 stages. So in the first stage, these two black holes are far away from each other. They move much slower than the speed of light. And their motion can be described by the Newtonian dynamics, or its modified version, the so-called post-Newtonian formalism. The gravitational wave in this stage has this sinusoidal oscillation behavior, basically with frequency twice as the frequency of the orbit. So as this system continuously emits gravitational waves, it loses energy and angular momentum, and then this binary separation gradually shrinks down. And when they're sufficiently close to each other, this post-Newtonian formalism just breaks down, and we have to use numerical simulations to describe the system and gravitational waves. So if you have questions here, I'll just redirect you to Professor Nanin. Okay. So after that, when these two black holes merge into a single one, then this final spacetime can be described by a rotating black hole plus perturbations. And these perturbations can also be described analytically by black hole perturbation theory. The gravitational waveform in this stage shows this decaying oscillation behavior. And that's why this stage is also called black hole ring down. So let's take a closer look at this decaying behavior and try to understand the physics behind it. Okay, so first there is a theorem in GR, the no-hair theorem, which claims that any stationary black hole can be the spacetime of any stationary black hole can be uniquely determined by its mass, angular momentum, and electric charge. So if we have a perturbed black hole, in general, it wants to lose its hair or the perturbations to reach the equilibrium state. So for stellar mass black holes, the process takes about 0.1 millisecond. It turns out similar process also happens for Kip Thorne, one of the founders of LIGO. And it took him like 40 years to reach the no-hair state. Okay, so astrophysical black holes, of course, do not carry charge, so they can be described by only the mass and the angular momentum. It turns out they cannot rotate absolutely fast, so the magnitude of angular momentum has to be smaller than the mass square, and this so-called reduced spin has to be larger or equal than 0 and smaller or equal than 1. So if A is 0, the black hole is non-rotating, and it's called Schwarzschild black hole. When A is 1, it's called extremal curl black hole. So in the ring down stage, we have a black hole, rotating black hole plus perturbations. These perturbations or hair are trapped near such black hole for a certain amount of time. Similar to the way that we have light trapped in an imperfect cavity. So the light has to bounce a few times before coming out. Also, just like these optical cavities have eigenmodes, these black hole cavities also have eigenmodes. And in this case, they are usually called quasi-normal modes. So in the ring down stage, these perturbations can be decomposed as a series of these quasi-normal modes. And they are actually the main reason why we see these decaying oscillations in the waveform. So how do we describe these modes? It turns out that similar to hydrogen atom in quantum mechanics, we can label the modes by their angular, azimuthal, and radial quantum numbers. And we can also perform the eigenvalue analysis and try to get the eigenfrequencies. In this case, the eigenmode frequency is complex because it describes decaying oscillations. So this omega r and omega I has to be both positive. This frequency can also be found numerically or through analytical method. For example, if we use the WKB method, similar to the way that we solve for the wave function in quantum mechanics, we can solve this eigenfrequency here. And in particular, we actually find a family of non-decaying modes for these extremal black holes with A equals to 1. So these modes have no damping rate. Omega I is 0. It's interesting because then it seems such extremal black holes who want to keep its hair forever. But there is no astrophysical process to make such black holes. But instead, according to the work by Novikov and Storm, if we have a rotating black hole and with a accretion disk, the black hole could be spun up to about A equals 0.998. We do have near extremal black holes. For those near extremal black holes, we can perform the mode analysis again. And we've actually found there is a family of slowly decaying modes with damping rate proportional to square root of 1 minus A. So if A is 1, then it becomes 0 again. So there is also interesting observational consequence with these modes. If we imagine that we have a near extremal black hole, we have some external matter source falling into the black hole. These matter sources will excite a series of these modes with different overtones, and the collective excitation of these modes will give us a power decay of the mode amplitude instead of the usual exponential decay as we expected earlier. So the math is actually simple here. So epsilon here is 1 minus A. So it turns out the summation of these exponentials coming from different overtones of the modes gives this expression. And when this square root of epsilon times t is small, this actually gives 1 over t at intermediate times. But when square root of epsilon times t becomes large, basically only the first term in this summation survives, and only the dominant quaternion modes with a fundamental overtone survives. And then we come back to the exponential decay again. So I hope sometime in the future they will observe this kind of power law decaying amplitude with gravitation wave observations.
Has anyone ever gone to higher order for near extremal black holes to see what the real decay? I mean, it must decay at higher order. I mean, if you're putting angular momentum into the black hole, then it's not really extremal anymore.
Yeah, so this is near extremal. This is not extremal.
Yeah, but in the extremal case where you found that it would never decay, has anyone calculated the next order correction to figure out what the decay time scale is?
Yeah, so the argument is if you excite such modes, it seems at a linear order this thing never decays. But then if you take this is a long story. If you take into account the back reaction of losing energy and angular momentum, you actually find that the extremal condition is always satisfied. So this is then it seems you could keep like you always become extreme. It is always an extremal black hole, but it seems that it will shrink its mass. So this cannot happen, right? You cannot just this is not quantum. This is a classical. You cannot just have a shrinking black hole. I think what's happening here is if you have a real extremal black hole, it's basically impossible to excite one particular this mode from outside. Basically, the mode excitation coefficient for a particular mode is 0 in that case. So, but yeah, it's like you're taking the limit. But if you combine all the modes, you'll still find this this behavior, 1/t behavior. But the contribution, each mode is infinitesimal small if we push it.
So just to make sure I understood, you're telling me there's an infinite class of extremal black holes with different hair. From what you said before, you can keep adding hair and it stays extremal. Am I understanding that correctly?
I'm trying to say that. Okay, so extremal black hole is a very weird object. So if you the mode of each individual mode of such black hole is very hard to excite, and if it's strictly extremal, you cannot excite.
But just from a mathematical perspective, I don't care how I make them.
Yeah.
You're saying that even when you include the back reaction, there are extremal black holes with
because
more hair and they stay extremal.
Yeah, so even if you include back reaction, I think so in this case, if you radiate, because this mode, the real part is omega is m times omega h. Omega h will be in the horizon frequency. So this condition is always satisfied, and it seems I think the extremal condition is always satisfied. Yeah.
Can people simulate extremal black holes?
I think numerically they try to push it to 0.99 or so. So what they have is they can prepare a black hole, a binary black hole, each one with 0.99. But after merger, somehow they find the final black hole has 0.95 spin, and they don't know how to make a final black hole to have high spin.
What if they just put in the extremal solution and run it on the code with small fluctuations?
There's
what
a
happens?
singularity at the horizon, so I mean it's not a very well defined.
So they just, okay, you're saying you just can't
No, yeah.
Maybe
not
Louis.
simulate them?
Yeah, you won't be able to put that one in. You could then use perhaps the idea that Andy has been pushing, right, the near string curve, and then write it as ADS2 cross S2 and then do the simulation there. That would be.
Nobody's done that.
No other questions? Okay, so all these discussions were based on the assumption that the mode amplitude is small. So we were working in the linear perturbations scheme region. So, but if the mode amplitude becomes large, then we have to also include the effect of mode couplings into the evolution equations for the modes. So let me discuss these nonlinear mode couplings, but let me start with the analog system, a fluid system. So we imagine we have a pipe, and we send some viscous fluid through the pipe. And then we can control the flow speed. So if the average flow speed is small, then basically we'll find that there are layers of flow. And within each layer, the flow speed is constant. But then if we increase the average flow speed, then we will observe that instabilities start to develop. And eventually, the fluid motion will become chaotic. So this phenomenon is usually called turbulence. And it's commonly seen in our daily life. So it's like in hurricanes or in those waterfalls. Okay? So in fluid dynamics, we can perform the mode analysis. And it turns out this turbulence happens if we have resonant mode coupling being stronger than the intrinsic mode damping. So in this way, the energy can be resonantly transferred between modes before damped away by dissipation. So if energy transfers from low frequency mode to high frequency mode, such as in these waterfalls or strong water waves, it's called energy cascade. And if energy propagates in the inverse direction, it's called inverse cascade. OK, so it turns out that black holes also share similar behavior. If we come back to the near extremal black hole, we can also find the resonant mode couplings between those slowly decaying modes, one with frequency twice as the others. So basically, the mode spectrum of these black holes will guarantee good temporal and spatial phase matching to ensure the resonant mode couplings. Also, this resonant mode coupling will trigger instability if the mode amplitude times the mode wavelength divided by the mode damping rate is larger than some number. So in fluid dynamics, there is a similar thing. So if the fluid speed times the fluid driving timescale divided by the viscous rate of the fluid, damping rate of fluid, is larger than some number, then the fluid will become turbulent. Apparently, these two criteria are quite similar to each other, right? So in this case, in fluid dynamics, this combination of numbers are called Reynolds number. And we can similarly define a gravitational Reynolds number for black holes. So once this turbulent instability is triggered for near extremal black holes, we will find that the energy will basically transfer from high frequency mode to low frequency mode, just like in hurricanes. And this instability also changes the geometry of the space-time, and it will also affect the gravitational wave emissions. It turns out that this analogy also has a deep connection with the holographic principle, the so-called gravity-fluid duality, which basically maps a gravity system and a fluid system in the ADS space-time and its boundary. So I'm not an expert in this, but we have plenty of experts in the audience, so I will not talk about that. But this is an example that similar physics can take place in totally different systems in nature.
It looks like you're going from low frequency to high frequency in this picture.
Yeah, so this is tricky. So if you look at the azimuthal direction, it actually goes from high. Yeah. So it cascades in this direction, but in this polar direction, it could be different. Yeah, could be different. Yeah.
So in three-dimensional fluid dynamics, you usually have a cascade from large to small scales. In two-dimensional hydrodynamics, you have inverse cascade from small to large scales. So is it because you do this actually on the surface here that you get the inverse cascade, or what's the deep reason for this?
So it turns out this here for black holes, it goes from high frequency to low frequencies because this instability is like it's a parametric instability. So basically, if you have oscillator, if you parametrically tune the frequencies to be twice as its intrinsic frequency, it will have this instability. And in ADS for ADS black holes, yeah. So for ADS 3+1 ADS black holes, you do observe inverse cascade in that case, because you have this gravity-fluid duality. On the boundary, you have 2+1 fluid. You have inverse cascade, and in the bulk, you have 3+1, and in the gravity system, you also have inverse cascade. In this case, you don't have this gravity-fluid duality, but it's still a 3+1 space-time. And what we showed here is, since you also have this inverse cascade here. Okay. So I've talked about these space-time dynamics and gravitational wave emission from binaries. Then I'll mention electromagnetic signatures in the strong gravity regime. So usually, electromagnetic wave could be a good probe for strong gravity physics, such as the Event Horizon Telescope that Professor Broderick is working on. On the other hand, if we look at the mergers of compact binaries, in many cases, they're both gravitational waves and electromagnetic waves. So it's important to understand the connections. So again, this is still a very broad topic, and it has many, many different systems. So I will pick one type of events, which is black hole jets. So these black hole jets are very, very energetic, and they are very common. They are commonly seen in our universe. For example, from stellar mass black holes in binaries, or supermassive black holes at the centers of our galaxies. So this is a simple illustration for a black hole with jets. And we have a rotating black hole, and we have a disk of accreting materials around it. This accretion disk will support a magnetic field which magnetizes this black hole. So as these materials fall into the black hole along the equator, then there is a funnel within which matters and energy are ejected away from the black hole. So within this black hole magnetosphere or jet, there are also plasma particles flying around. They can come from these accreting materials, or even from vacuum polarizations. These black hole jets are also fluctuating in time in reality. So we shall first talk about their stationary limit, and then discuss the fluctuating waves in those jets. So in the stationary limit, how do those ejected matter gain energy at the first place? It turns out there are two candidate sources. The first source is an accretion disk. Well, these charged particles can be accelerated while the so-called process of magnetic reconnection. The second source of energy is the black hole itself, and it turns out that it can power the jet with its own rotation energy. So let's focus on the second source, because this is actually a relativistic effect. So let's imagine we have a rotating black hole, and then we throw a particle into it. After some time, this particle undergoes some kind of explosion, and it bifurcates into two parts. One part falls into the black hole, the other part goes to infinity. So parallels show that the part goes into the black hole could have negative energy, such that due to this energy conservation, the part escaping to infinity has more energy than the energy of the originally injected particle. So in this case, the black hole actually decreases its rotation for a bit to supply actual energy for this escaped particle. And this process is called Penrose process. And it has many applications. For example, Professor Avanitaki used this process to argue for this amplified QCD axioms around rotating black holes. On the other hand, Bamford and Janak, I don't know what's happening here. Bamford and Janak applied this mechanism for rotating black hole with plasma and magnetic field. And they argued that this black hole could launch a jet in that scenario with its own rotation energy. So when this energy is extracted from, after the energy is extracted from the black hole, it can be then converted to electromagnetic radiations at different frequencies in the jet. For example, at places where the particles can be accelerated along the field lines and then scattered with the environmental photons. But the detailed process is not completely understood yet, so I'll not talk about that part of physics. The bottom line is the electromagnetic configuration of the magnetosphere is crucial to understand this jet structure and this energy extraction process, and ultimately this energy out conversion process. In the past, we have many numerical solutions available, but they're much less analytical understandings, partially because here the field equations are highly nonlinear. But in certain cases, we have additional symmetry in the system, which help us to understand the system. For example, in the case of near extreme curve, it turns out that there is a additional conformal symmetry near the horizon of such black holes, and we can use this additional conformal symmetry to classify different jet solutions near the horizon. But this is just a special example. In general, if we have a rotating black hole and we have plasmas, and if we have external driving magnetic field, how do we describe the magnetosphere near the black hole is still an open problem. Okay, as I mentioned earlier, the real jets are fluctuating in time, so we have to understand this dynamical behavior of jets or black hole magnetospheres. It turns out that similar to the way that we analyze the mode for vacuum black hole, like we analyze the quasinode modes, here we can also perform the mode analysis to study the modes of black hole magnetosphere. It turns out this black hole magnetosphere will oscillate in two different ways. So following the first way, these waves will just propagate along the.
Is there a disk here?
There is no disk. There is only plasma and black hole.
Okay, so it's a uniform magnetic field everywhere? Is that?
It doesn't have to uniform magnetic field.
So what is the magnetic field?
So you could have different configurations. You could have a uniform driving magnetic field, but then near the black hole, the magnetic field is no longer uniform, right?
I'm just, in real situations, you have disks that are, I guess, responsible for.
Yeah. So
if there is no disk, then there is no jet. So I'm trying to understand what's happening.
So yeah. So there is a external boundary condition for the magnetic field. It could be uniform, non-uniform. Yeah. But I guess in actual physical scenarios, we can approximately assume it's a uniform driving field from the disk.
So the magnetic field is usually brought in by the disk, by the accretion disk. But here you don't have an accretion disk.
Because I want to look at the field distribution near the black hole.
Okay, so somehow you can ignore the disk near the black hole. So you're using force free?
Yeah, I'm using force free. Yeah.
So presumably somewhere close to the equator, then this breaks down.
Yeah. So near the equator, there's this is so-called current sheet.
Okay.
The plasmating breaks down. Yeah. Yeah. So so following the first way, these waves propagate along field lines, either escape to infinity or they just go into the black hole. So in the short wavelength limit, if we look at some local Lorentz frame, actually these waves are the same as the so-called Alfvén waves in plasma physics. Following the second way, the waves are trapped near the black hole for a certain amount of time before they decay away. They're very similar to the quasi-normal modes of vacuum black holes. And if we look at the short wavelength limit and in the local Lorentz frame, these waves are the same as a fast magnetosonic wave in plasma physics. So now here, these two family of modes actually characterize the fundamental oscillation modes of a black hole magnetosphere in a curved spacetime. So how do we generate these waves or modes? So it turns out one way to do that is to perturb the spacetime itself. For example, by sending gravitational wave into the plasma or having moving masses in these magnetized plasma. We can actually try to imagine an interesting scenario. So let's say we have a binary black hole merger within such magnetized plasma. So in the ring-down stage, as we discussed earlier, the spacetime can be described by rotating black hole plus quasi-normal modes. These quasi-normal modes will try to shake the black hole jet, and this will create a time-dependent piece in the luminosity with frequency being the quasi-normal frequency. On the other hand, there could be another time-dependent piece in the luminosity, which corresponds to the fact that the jet wants to oscillate with its own eigenfrequency, the fast wave frequency. So detecting this oscillating piece in the luminosity spectrum will provide us a method to measure let's say, the black hole mass or spin. And this is also an example of using electromagnetic observations to probe strong gravity physics, as this observation is connected to these gravitational waves emissions.
So can I ask you a question?
Yeah.
I'm a bit confused. So you're talking about Hoffman waves, but are there Hoffman waves in the force-free approximation?
There are. So we find two. So in the short wave length limit, they basically just become either Hoffman waves or fast magnetosonic waves. But the thing we're doing here is study the global modes of magnetosphere.
Yeah, I guess what confused me. So in Hoffman, the speed is like a square root of, I guess, bs squared divided by the density. But then
in the relativistic limit, basically that becomes the speed of light.
Just the speed of light.
Yeah.
Okay.
Yeah.
Right.
Okay, so I've discussed the detector physics and the application of these detectors in study fundamental physics. Also, I discussed the space-time dynamics and gravitational wave emission from binaries and the EM signatures in the strong gravity regime. So let me just wrap up. And let's try to imagine what will happen in the next few years. So basically, advanced LIGO will continue to upgrade up to, let's say, 2018. So before that time, maybe a Nobel Prize will be given for this finding already. So when it finishes upgrades, we are talking about more than 100 events per year. We will be able to do a lot more cool physics with it. For example, we should be able to study electromagnetic counterparts of gravitational wave emissions. We can test general relativity in a strong gravity regime. And after that, advanced LIGO will be upgraded again to advanced LIGO Plus or even LIGO Voyager. So then we are speaking about sources at cosmological distances. And around that time, we are also likely to have observations from those space missions or pulsar timing measurements as well. And that means the gravitational wave astronomy will enter the stage of precise measurement, and that will allow us to have more understandings of fundamental physics or cosmology. So before the end, let me mention a small story about Feynman. So after a gravity conference in Warsaw in 1962, Feynman complained to his friend. He said, "I'm not getting anything out of the meeting. I'm learning nothing. Because there are no experiments, this field is not an active one. So few of the best men are doing work in it. The result is that there are hosts of those here, and it's not good for my blood pressure. Remind me not to come to any more gravity conferences." Apparently, Feynman was not satisfied with the status of gravitational research at that time. But now my question is, with all these fascinating developments in gravitational wave physics in the past 30 years, if Feynman was still alive, would he change his mind by coming to gravity conferences again? This is my guess of what he would say. OK, that's it.
Questions? John?
How do you award a Nobel Prize to 900 authors?
OK, so my guess is it will be given to Kip Thorne, Revise, and Ron Giger, because they're the main founders of LIGO. But others might disagree with me. But I hope it's given to this.
So really, this blew me away when you said that the quasi-normal modes stick to external black holes. Now, if you combine that with this inverse cascade that you found, if you go really close to extremality, then all those modes are going to stick to the black hole. They're not going to ring down. So what's the end state of that instability? Does that suggest that in the in the limit of extremality, there's actually another solution to Einstein's equations?
Sorry, are you talking about the nonlinear instability?
Yeah. I mean, it must go somewhere, right?
It's a so it's a transient instability. It actually only happens for a certain amount of time. So when the amplitude of the driving mode, it will decay, slowly decay. When it's smaller than some amplitude, then this instability just stops.
So you only get it if you have driving.
Yeah.
Thank you.
Any other question?
So what electromagnetic signatures are you thinking about? I'm thinking about the last part of your talk. So
I was talking about the total luminosity. In fact, because we don't really have a good understanding. I mean, there are models such as the gap models which try to explain why we have, let's say, gamma ray emissions from the jet or X-rays, but we really don't have a good understanding of that. So it's safer to say that there is a variation in the total luminosity, and it's more difficult for me to predict what will be the spectrum for each frequency.
Yeah, I guess I'm just thinking, I mean, their astrophysical observables are come from much farther out. I mean, the jets that we see, well, I guess some of them we probably can see maybe in radio farther in, but I mean, most of them just see signals from much farther.
Yes. In the past, where the more observations are from this emission regions far away from the black hole, but now we have better ability to localize the emission regions near the black hole. I think there is a Nature paper last year or something like talking about localize the emission region actually very close to the black hole.
So one question on your electromagnetic modes in your dynamo jets. Are they isolated near the black hole, or are they actually basically asymptotically far away?
Sorry, can you repeat?
For the modes basically that are sitting there, the SAM mode and alpha mode. Like, in what environment are they sitting in? Are they sitting close to the black hole, or are they sitting further away?
Yeah, they're mostly close to the black hole. Yeah.
So then in that case, basically, for your coupling between the quasi-normal modes and the fast mixing side modes, the alpha modes in that case, that coupling does depend on the structure of the alphane waves, then, does it not? So how do you calculate the coupling between the quasi-normal modes and the alphane modes?
So here, I'm not even talking about the coupling between modes yet. For example, this is basically, for example, the quasi-normal mode of the space-time shakes as more or less stationary jet. It's a driven oscillation, so this is our linear.
Just linear there.
Next question.
Coming back to these electromagnetic signals, if you're going for something which is rapidly variable in electromagnetic signals like pulsars, you often have the problem that propagation sort of affects the coding. So you have refractive scattering and so on and so forth in terms of inhomogeneities in your media. Is there an analog for that? I mean, if you're sort of propagating gravitational waves to a medium where you have sort of an inhomogeneous field like perturbers, stars, and so on and so forth, where you would have scattering of those gravitational waves as well?
Yeah, so I'll answer this question in two different perspectives. So first, in principle, there is, okay? So in principle, if you have some dust, when gravitational wave comes in, you will shake the dust, and this will generate secondary wave, and also scatter wave. But compared to electromagnetic wave, this is extremely weak. And
if you were scattering off, say, a star, it's still a potential long-run star. I mean,
it's still very weak. So the coupling between gravitational wave to matter is extremely small, and that's also why this gravitational wave observation is important, because there are many astrophysical environments that are opaque to electromagnetic waves, but gravitational wave can just go through with very little damping. Yeah.
Okay, let us thank Juan again.
Thank you.